Good morning, and I want to say thank you to the organizers. I've been having a wonderful time visiting Spain for the first time, and first time at an IAH Congress, and enjoying this very much as well, so thank you so much. I'm going to be talking about climate change effects on groundwater. Of course, it's a little bit difficult to separate sometimes the climate change impacts from direct human impacts, so I'll talk about those as well. I have many co-authors who have contributed, some listed here, others not, but I've tried to reference important papers along the way. So let's talk first a bit about groundwater storage variability at large scales. On the left here is a famous diagram from Stanley Chanyan showing the relationship between precipitation, runoff, soil moisture, stream flow, and groundwater, and just sort of demonstrates in a conceptual way how an anomaly in precipitation sort of works its way through the hydrological system, and groundwater is slow to respond and typically has smaller variability than the near surface components of the water storage. We can see this as well if we look at a time series where we have good data, good ground-based data, in this case in Illinois, which is a state in the US. And you can see here, this is a time series that runs from 1983. I don't see that very well. Well, it runs from 1983 through roughly 2005. The blue on the bottom is the groundwater storage. The red is soil moisture, and white is snow. And you can see that the soil moisture variations are the largest on a seasonal basis, but on an interannual basis, the groundwater storage variations can be as large or larger than the soil moisture storage. This is in Illinois, which is sort of mid-latitude temperate region. In other parts of the world, you're going to have different sources of variability in this terrestrial water storage column. So, for example, if you're in an alpine or high latitude region, then snow and ice might be the largest components of terrestrial water storage variability. If you were in someplace like the Amazon, a humid tropical region, then the surface water storage might be the largest component of variability. The other point I want to make here is that if you look at the sort of top contour, when you add up the groundwater, soil moisture, and snow, the top contour would be the terrestrial water storage. Let's see this. There we go. The top contour is the total terrestrial water storage. And when I talk about GRACE later on, what GRACE is able to measure is this total terrestrial water storage anomaly or changes. So how do these components interact? Well, it's interesting to see here. Maybe if I can make this run. Usually there's a little bar that I can press a play on. Does anyone know where the... Okay, well, if this were to animate, which would be cool, then you would see that the yellows and reds are the precipitation. They move along very quickly over the surface, and the blue, which is the soil moisture, would be sort of reacting to that and moving more slowly. And so you'd see the precipitation sort of paint the surface with some wetness, and then that wetness would remain for a little while and then slowly sort of go away. Disappointed this won't run. Any thoughts on that? Usually there's like a bar that shows, oh, thank you. No, didn't you have to click on it? Perfect. Okay, so now you can see what I was talking about. You see these precipitation events circling through very quickly. Time is in the lower right there. And like I said, the land surface is sort of painted with wetness, which remains for a little while until evaporates and some of that water maybe recharges the aquifers. Now, if we look at the relationship between between the soil moisture and the shallow groundwater, or the undefined groundwater. Now, this comes from a model, so you can take it for what it's worth, but you can see a similar sort of situation where the soil moisture, which is in more or less direct communication with the atmosphere, things change very quickly. It might be dry, one day, and then suddenly you have a wet event, and it goes from dry to wet. Whereas the groundwater variations sort of move around like blobs. It gets wetter and drier, and things move around slowly. And you can see the effects of droughts that take hold in a region, and then the groundwater slowly depletes, like right now in Texas and the southern U.S., and then over time it recovers. But it's a much more slow variation, and also in that way sort of preserves or integrates the longer-term meteorological variability. And for that reason, groundwater is likely to be a useful indicator of climate change. So I'm sort of saying that here. Groundwater varies more slowly. It also has a larger range of variability than some of the other components of terrestrial water storage, like soil moisture. So the soil moisture might be in the top few meters of the soil. There's a limited range of variability. It's eventually, if you have a drought that lasts for a couple months, that eventually it's going to be dry. You can't lose any more water, or there's just only a certain amount of water it can hold. But as you know, with groundwater, these aquifers, especially deeper aquifers that are unconfined, there's a very, very large range of variability. So you can imagine with climate change, if it happened to be causing the groundwater storage to increase, you might have a long, slow increase in groundwater storage with water tables rising. And the opposite might be true if the climate change was causing the water storage to be reduced. So what's anticipated for the future with climate change and groundwater recharge? There have been a few papers, and they're more or less speculation and hypothesis, based on what we know about changes in groundwater on shorter periods. This is a slide from a Taylor et al. Paper that I just found out that Alan can actually be credited for, showing some of the key interactions with groundwater, things like there might be an increased seasonality, flows from the surface water fed irrigation. So it's not just the climate change impacts shown here or represented here, but the direct human impacts like irrigation. And you might have things like increased evapotranspiration, which end up reducing the recharge. Other papers have shown similar things. This is another one from Meissner et al. Showing anticipated effects of climate change in groundwater in the western United States. Some of the things that might be anticipated are things like less of the precipitation falling as snow, which means there's less time for the water to sort of sit there and slowly melt and percolate and drain into the aquifer. Therefore, more surface runoff. Therefore, you have more water recharging the aquifer through these streams and rivers than you would have through the mountain fronts. As I mentioned, direct human impacts are going to be involved with the climate change impacts. Hard to separate, although we know to some extent what's happening now in terms of direct human impacts. This is from a paper by Yoshi Iwata, showing different regions of the world by combining observational data and models, showing different regions of the world that are being affected by human water consumption and withdrawals of groundwater. And the chart on the right shows, top line shows the global water demand, and then the second line, the middle line, shows global groundwater abstractions, and then the bottom line is global groundwater depletion, and these are continuing to rise over time, so definitely something we have to be concerned about. Saw this chart earlier showing the effects of agricultural and food trade. Of course, as Alan mentioned, it's not just people going out and pumping a little bit of water to drink. The main impact on groundwater is going to be the agriculture. Somewhere between 70 and 80% of the water consumption is related to agriculture. And this paper by Dolan et al. Shows in different parts of the world which food crops are causing the depletion and how they're being shipped around from different countries of the world in the form of virtual water. So let's look at the large-scale groundwater science. How do we do that? In the 20th century, we're almost completely reliant on in situ observations. So we have piezometers, we do pumping tests, well drilling logs, maybe some ground penetrating radar, other geophysical methods, and then some groundwater flow models that typically are either local scale or crude large scale models. And you can do some interesting science with this, of course. This is from a paper that Peiling Li published recently looking at data available from the USGS. Some of the subbasins of the Mississippi. And if you look, for example, at the upper Mississippi River Basin, chart showing on the right, the orange is all the various groundwater hydrographs from the wells in that region. And the black line in the middle shows the average of those. And we're able to see things like the drought, a major drought in 1988 in the central U.S. And then in 1993 there was flooding, and that's represented in the groundwater. But ultimately, these in situ observations, unfortunately, we really just don't have enough of them. So even with other variables, things like meteorological stations shown in the upper left, this is the global telecommunications system. This is what a lot of weather forecasts rely on data from these stations, and it's the network's very dense over the more populated, wealthy parts of the world. But then if you look at a place like Northern Africa, you could go 100 kilometers between points. Similarly, if you're interested in runoff, the Global Runoff Data Center houses these observations, seen in the lower left. The blue colors mean that the data are more recently updated. The yellows, oranges, and reds means it's been 10, maybe 20 or longer, more years since the last observation was provided to the Global Runoff Data Center. And then if we look at groundwater observations, some parts of the world, like the U.S., we have a decent number of observations. This is a map on the lower right from the USGS showing their groundwater climate response network, which is the wells that have a long time series that are frequently observed, long and frequently enough that you can say something about climatic variability. It's pretty dense in the eastern U.S. In the western U.S., less so, but it's still much better than what we get in the rest of the world. The upper right, I have to replace the map in the upper right after talking with Nano yesterday. The IGRAC and the Global Groundwater Monitoring Network now have data from, I think, 17 countries, he said. And by the way, they are not a data storage house or provider. They're there to promote research. But the point remains that most countries of the world, you cannot get access to groundwater, in situ groundwater data for various reasons. There maybe they have the data, and those data have just not been digitized or centralized and made publicly available. Or it could be a political issue. Maybe they don't want their neighbors knowing what they're doing with their groundwater. In any case, it's very difficult to get groundwater data in much of the world. So these in situ observations and the techniques of the 20th century are still very important, still critical to have as many in situ groundwater observations as we can put our hands on. But in the 21st century, we do have some other options which are valuable. So first is remote sensing. I'll talk about GRACE and satellite gravimetry. There are other techniques, including synthetic aperture radar, which allows us to measure the changes in height of the land surface, and those can be related to the water stored in confined aquifers. And then we have models that have been improved because we have just more powerful computers these days, and people with graduate students who have the time to improve the models. So they might have 3D groundwater flows and larger scales than we were previously able to run. And of course, then we can not just have groundwater models, but have models that are coupled to the other components of the hydrological system, the surface layers, and the meteorology. So GRACE, or NASA has many satellites. NASA is not just looking at other planets and other stars, but has a significant Earth science component to it. These are the current NASA satellites that are circling the Earth, making observations, and many of them are highly relevant to hydrology. And I've circled some of those. I'm going to focus again on GRACE and GRACE follow-on. And of course, ESA, JAXA, India, they have their own space agencies with other satellites that are also contributing to this. So let's talk about GRACE and GRACE follow-on. So first of all, GRACE is the Gravity Recovery and Climate Experiment. GRACE lasted from 2002 to 2017, and GRACE follow-on launched last year, so we have another pair of satellites. And what makes them different is that while most remote sensing systems, most satellite remote sensing systems have instruments that are basically looking down at the Earth. They're measuring either emitted or reflected wavelengths of light. Different wavelengths, as you can see in the upper right, are useful for measuring, estimating different quantities, things like soil moisture, vegetation, snow, etc., rainfall. But when you're looking downward and using these types of radiation-based techniques, you can't penetrate between lower than a few centimeters below the surface. So not really useful for groundwater. GRACE and GRACE follow-on are completely different. So instead of looking downward, both of these missions had a pair of identical satellites that are actually looking at each other, meaning that they have a microwave, and now GRACE follow-on, a laser ranging system that measures the distance between the two satellites, and as I'll show you, enables monitoring of the gravity field, which then enables monitoring of terrestrial water storage variations, and then means there's no depth of penetration issue. The deepest aquifer can still be resolved. So the way this works is, as I said, there are two satellites. Imagine there's a gravity anomaly, something like a mountain range. So there's more mass in the mountain range than there is in the surrounding area. And more mass means there's more gravitational potential. So as these two satellites are floating along around the Earth at about 500 kilometers altitude, the first satellite's going to feel that gravitational anomaly first, and it's going to be pulled forward, and the separation between the satellites is going to increase. And so every 5 seconds, that distance, which is about somewhere between 100 and 200 kilometers, they're free floating. So imagine you have a 100, 200 kilometer distance. Every 5 seconds, you measure that distance down to about a micron, which is about the size of a red blood cell. So it's an incredibly precise measurement of this intersatellite range distance. And we put all these measurements, orbiting the Earth, all parts of the Earth. They put all these measurements over the course of a month into a big supercomputer with a regression model. You can produce a map of Earth's gravity field. And from month to month, those gravity field maps are so accurate that you can see changes in the maps. And those changes are caused by changes in mass around the Earth. So why does mass move around the Earth? You get things like ocean circulation and tides, atmospheric mass. So when we take an atmospheric pressure measurement, that's measuring really the mass of the air column above us. And then over the land, the changes in mass are changes in the terrestrial water storage. So you have a big snowstorm, for example, you get some snow. That snow piles up in the Earth. There's a lot of mass in that snow. And it's enough mass that it can actually perturb the orbits of satellites in a way that we can measure and then infer how much water was there to cause that change. So when we do this, when you get these monthly maps and you remove the effects of the atmosphere and you remove the effects of the ocean using observations and models, what you come up are the changes in the terrestrial water storage. And so the left shows the terrestrial water storage anomalies in units of centimeters. So a terrestrial water storage anomaly is a departure from the mean. So GRACE cannot tell us the total amount of water at any given location. It only tells us how it changes over time. So we look at this relative to the long-term mean, and we see what you see on the left largely are seasonal cycles. There are wet seasons and dry seasons in most of the world. And a place like the Amazon has huge variations in terrestrial water storage. And then a place like the Sahara Desert, almost no variations in terrestrial water storage. And then if we want to go deeper, we can remove that seasonal cycle and then look at the interannual variability, and that's what's shown on the right. So after we've removed that seasonal cycle, on the right you see these non-seasonal terrestrial water storage anomalies. So these are the effects of things like droughts and floods and that sort of thing. So after we remove the seasonal cycle, one thing we can do is we take the GRACE data for basically the entire period of GRACE, in this case from 2002 to 2016. We've removed the seasonal cycle, and then at each location on Earth, we fit a trend. We just fit a linear trend at each location, and this is the map we get. So areas where water has on average been increasing are shown in blue, and where it's been decreasing shown in red. And it's up to us as hydrologists to try to interpret which of these apparent trends, I'm not going to call them, they're actually trends, because some of them might just be natural variability, which apparent trends are caused by natural interannual variability, which are caused by water management or mismanagement, and which ones are maybe caused by climate change. If you want to look at natural interannual variability, a good thing to do is look at the precipitation. The upper right shows percentage of normal precipitation during the observation period, and the lower right shows the precipitation trends during this period. And you'll see that there are some areas where precipitation has been increasing or was higher than normal during the period, and we see a corresponding increase in terrestrial water storage. Similarly, areas where water's been, where precipitation has been less abundant, and we see a decrease in terrestrial water storage. So we can say that perhaps these areas are just, in part, the changes are caused by natural variability. What can we do for climate change? It's a short time series. It's hard to say with any certainty what's caused by climate change. But if we look at what's predicted, in this case, the IPCC RCP 8.5, which is the high-end scenario, there are areas where precipitation is predicted to increase, and we see perhaps an increase in terrestrial water storage during this time period. Again, it's a short time to be looking for climate changes, but we're starting to see perhaps some indications that these things are coming true. Similarly, areas where precipitation is predicted to decrease, and we see decreases in terrestrial water storage. And then, of course, the water management and mismanagement. So as we've been talking about, irrigated agriculture is the big consumer of water, fresh water. And if we look at the areas where there's intense irrigation, they tend to be well aligned with areas where there's significant groundwater or terrestrial water storage depletion. Of course, a lot of this terrestrial water storage, when you're looking at a big trend like this, it's not going to be soil moisture. It's probably going to be the groundwater storage changes. So areas of decline, but also it's interesting to see an example where the Three Gorges and other dams have been built by China. There's actually an increase in terrestrial water storage that we can measure using GRACE. So, all these emerging trends in freshwater storage. One of the first ones we noticed was in northern India. Alan talked about this a little bit, and when we look at this area, shown in this sort of rough triangle, we can estimate that they've been losing about 19 cubic kilometers of water per year. And this is obviously groundwater. What's happening up here, they're growing a lot of wheat and rice, which are water-intensive crops in an area that's basically semi-arid. They pump this water out of the ground, they put it on the surface. Most of it, or a lot of it, evaporates, and you end up with depletion. 19 cubic kilometers per year is a lot of water. We saw yesterday that we lose about, or that Spain reservoirs, total reservoir storage in Spain, I think, was 53 cubic kilometers of water. So every 2.5 years, northern India is losing about that much groundwater. And by the way, in estimating this using GRACE, the issue in India is not data scarcity. This map, all the little tiny dots on this map show the hand-dug wells and the piezometers, so they're all over. It's a huge network. But those data are not publicly available unless you live in India or unless you have a colleague who's in India. And this is this emerging trends map from GRACE, and we tried to explain all of the major changes in terrestrial water storage that we saw during this 14-year period as caused by either natural interannual variability, climate change, or direct human impacts, or some combination. And if you're interested in this map, I'm not going to go through all these, but if you're interested, we published this in Nature last year, emerging trends in global freshwater availability, and encourage you to take a look. So here's my summary. I'm running out of time for questions, so I think I may just leave this up here and take questions, and you can read it as I answer them. Thank you.